I think we can start. Okay, so let us start. Now, last week we looked at the introduction part of constructing elliptic curves. And today we're supposed now to look at how do we construct elliptic curves using the complex multiplication method. That's a method we'll be using today. So last time again, so we were doing that introduction part, we looked at how to get the trace and then the J invariant. And therefore today we'll be seeing how then we use those two in coming up with the correct equation for the elliptic curve. Now we said that this is very important because at this point, what we want for security reasons, a company would want to come up with an elliptic curve that meets its specifications. So if it wants some parameters to be met by the elliptic curve, then it has to come up with that elliptic curve on its own from the scratch. And so that's what we'll be doing today, so that we see how to come up with elliptic curves from the scratch. Now, so before you come up with the elliptic curve from the scratch, you have to know what order you want. What order you want your elliptic curve to have how many points. So that one you must have it in mind. And then after that, then if you know what order you want, then that means you have a prime number. Supposing the order is not prime, so we talk about prime factors and so on if the order is not prime. But in most cases, the order, okay, that is the order of the number of points. The number of points is not always that they should be prime. They can be even composite. Now, and then you have again to know the base field, the field you want to work with. So for instance, I can say, I want my elliptic curve to have 20 points, and I want it to be in F13. So you just choose these two, and then you begin working now. That means you'll now find the trace, for this, and then find the J invariant, the way we did. And then there are a few things I'll show you now. After you have the trace and you have the J invariant, now how do you proceed to come up with the equation of the elliptic curve? That's what we'll be looking at today. So it's not just choosing an elliptic curve from online. No, a company comes up with its own elliptic curve that it wants. Now, so the process of coming up with elliptic curve begins by one, choosing the best field, as I've said. You want to, for instance, your elliptic curve to be in F13. So after that, after choosing that, now how do you choose this? How do you choose your field? Your field must be chosen such that Q, this Q, so you don't just choose it like that. You don't just choose, it has to meet some conditions also, that this Q here. Q must be such that it's equal to P raised to M, where P is a prime number and M is an integer. just any, and P can be any number. For purposes of our discussion, we'll be picking P to be any number, any prime number greater than 3. Greater than 3. Now, what about M? Then we will see what M is. But M is also just an integer. Just an integer. So that's how you choose your Q. You choose such that it can be expressed in this form, where P is a prime number and M is just any integer. For instance, if I want to, I can choose a prime like 5 and maybe raise it to any integer. Let me say raise it to 1. So if I raise it to 1, it means my field that I've chosen is F5. But I can also have F raised to 2. M is just any integer. So that my field, therefore, I'll be talking about F25. So M is any integer and P is a prime number. Now, like the one I've been talking about, F13, so it means they have chosen P to be 13 and M to be 1. So that's how you choose. That's how you choose. You don't just choose, there must be a prime number somewhere. Then that prime number is raised to another integer for your choice of Q. And remember, this Q is the base of the field you want to work with. Now, after choosing the field, after choosing the base field, choosing Q properly, as we just explained, you now want to calculate the trace. You want to calculate the trace the way we did last time. And one thing you must remember is that the trace, okay, you'll just choose. You may choose the trace, not necessarily calculating. You want to choose, because for you to calculate, how are you calculating the trace? The trace we're calculating by the number of points. Okay, the number of points. Like for instance, 20 is equals to, and we see we've not already chosen how many points we want. But now, how are we getting this? Was 13, let me say plus 1, then minus t. Minus t, where 13 is the base field, is our Q. And then you add 1, then you subtract t. So after getting your t, let's say you calculate it, let's calculate it then. Then after you get t, but this t is after calculating, again, you'll have to, as we've been looking at examples, you might get several t's. You might get maybe plus or minus. You might get, for instance, there's a case you can get -6, but when you check, you discover -6 will not work. So you choose 6. But I'll show you an example. Now, so after getting t, what property must t meet before you even proceed? We've chosen our p here. We've chosen our p above, the prime number. So what about this t? T must be coprime to p. The GCD of p and t must be 1. If that is not the case, then p is not correctly chosen. If the GCD is not 1, then P is not correctly chosen. That means you have to choose again. Now, so T must satisfy this condition. T must fulfill this condition that the GCD of T and P is 1, and the other condition T must satisfy is that it must be less than or equal to 2 multiplied by the square root of q. We chose q here. We chose q when we were choosing the field we want to work with. So T must also, you can see there's a relationship between T and Q again, and the relationship is this. So T should not be greater than this number. It must be in this range. So this is just a range. T must be in the range 2, and then this side negative 2. So T should be less than or equal to. Should be less than or equal to. That's the condition, not greater. So it can be less than this number, or it can be equal to that number. The maximum it can be is that number, but it cannot be greater than this. It's either less or equal to. That is a condition. Now, so T must meet these 2 conditions. T must meet these 2 conditions. So when we'll be calculating T, we'll be calculating, of course, we'll be getting the trace. But after getting the trace, we must ensure that it meets this condition. If it doesn't, then what we've calculated is not the trace. We have again to pick another trace. Now, I talked about Hess bound last time. Hess bound tells us about, it tells us that the number of points of the elliptic curve, and let's call the number of points to be R, the number of points of the elliptic curve must be in the range P plus 1 minus T. Then again, this side, P plus 1, then minus T. So it must be in that range, but it's written here properly. It's written here properly. This is the Hess bound. That the number of points of the elliptic curve must be in this range. Must be in that range. So they can never be, and we saw that last time when we were doing our examples. We saw that the number of points of the elliptic curve are very close to the field, the base field, very close to the base field. That's what Hess bound says. That if the base field is 5, then you expect that the number of points are just very close to 5. And when we did that last time, we discovered that when you're looking at the curve 1, 1, the number of points were 9. So they're not very far from this. So they must obey this. Where T, in our case, we found T last time. I don't remember what it was, but I think it was 9 is equals to 5 plus 1 minus T. It was 3. T was 3. No, T was negative 3. T was negative 3. So if I put negative 3 here, this will be 4, then plus 2 root 9. And this other place, it will be 4 minus 2 root 9. So you find that the number of points, which are 9, are in this range. Not root 9, root 5. So root 5. Not root 9. So root 5, the base field. So the number of, because root 5 is just approximately 2 point something. So 2 point something, let me say 4. Subtract from this. Is it 2 points? Yes, it's approximately 2 point something. The answer you get multiplied by this, subtract from that. Then this again, approximately 2 point something. The answer you get, and then again subtract add to that. So you discover that they need to fulfill the Hess bound. But now, that is not what we're interested in today. What we're interested in today is how do we get the elliptic curve. Let me just recap what I've already said. I've said for us to come up with the elliptic curve that meets conditions that we want, the first thing we do, we choose the field we want our elliptic curve to be in. So we choose, for instance, we want to work with F5. So we want our elliptic curve to be defined in this field. So once I've chosen this field, and of course, choosing this field, we've said that this base, our Q, must meet some condition. It must be such that it's equals to P raised to M, where P is a prime number and M is just an integer. So Q is chosen so that it meets this condition. After choosing Q, the next thing you choose is the trace. And you choose the trace such that the trace is coprime to P. Is coprime to P, this P. And that is one condition. And the other condition is that the trace must be less than or equal to 2 multiplied by the square root of Q. So there are two things here. You've chosen, first of all, you choose Q and P. And then after that, you come and get the trace. Now we have the trace. But there's something before we proceed. I've said, carefully choose the trace to ensure that the curve has a large prime order. So that is if you're doing it for practical reasons. You want it to apply it. If you want it to be applied in real life situation, this is how then you choose that the curve would have a large prime order. In other words, the curve would have large prime number of points. Now, so T helps in that way. T helps in that way. The other way that T helps, and of course, is in the calculation of the embedding degree. And in our previous lessons, we've seen how the embedding degree is very necessary. So your choice of P and Q will also determine your embedding degree. And we define what embedding degree was. Okay, so let's now go into the next step. The first step, you just said choose your field. Choose your Q. A Q such that is equals to P raised to M. Then T. Then after you've chosen those ones, the next thing you do is to get the J invariant. But before that, let's find the discriminant and the Hilbert class polynomial. So these are not very complicated. The names might appear complicated, but now when I explain, you understand what it is. Now, for this method we want to do, our method is a complex multiplication method. And for it to work, the Q that we've talked about and the T that we've talked about above cannot just be chosen at random. You don't just choose them randomly. They have to meet some conditions, and the conditions, I've now put the conditions here mathematically. I've put the conditions mathematically. You don't just choose them. As I've said, they are not chosen arbitrarily. Now, they meet some conditions, and the conditions I've already explained, but now, mathematically, I want to bring in the discriminant. So they must satisfy specific conditions so that two integers, D and V, exist. When you what I mean is that when you choose Q and T, you must choose them such that they will exist these two integers. They will, you see, you might choose a Q that will not give you these integers, and we'll be seeing it. Consider that your choice would give you these two integers, D and V, where D should be less than 0. That is one way. And then D must also be congruent to 0. Or 1 mod 4. So your choice of Q and T determines that you should get a D, and that D should be less than 0. And again, it must be congruent. If it's not congruent to 0, then it must be congruent to 1, mod 4. And for Q, 4 times the Q you choose must equal to T square plus this D here, plus this D multiplied by V square. Now, this is absolute value of D. This is absolute value of D. Remember that D was less than 0. So if it was less than 0, it is negative, in other words. So I'm taking the absolute value so that I get the positive value. So that if it was -2, the absolute of that would be 2. Then that absolute value multiplied by V square. So this formula here is supposed to give me V. This formula here is supposed to give me V, and then it's supposed to give me D. So it's from this formula that I get V and D. Remember, I just chose Q and I chose T. And then I'm now saying that after choosing this Q and T, I write this formula. When I write this formula, I substitute my Q and substitute my T, and now check what will be my D and what will be my V from that after substituting. Of course, we look at an example how that is done. So you can see you're not just choosing your field just like that. There are conditions it must fulfill. Remember why we began. We began by saying that your choice of Q must also be such that Q should be equal to P raised to M. But now we've gone further again to say this is not the only condition. The other condition, and of course we say that T, your choice of T again should be such that this T is relatively prime. It's relatively prime to P, and that T must satisfy the condition that it's less than or equal to 2 multiplied by the square root of that. And again, this is not the only condition for choosing T. So we are going further and saying that the choice of T and Q must help you to get D and V, must help you to get D and V. So that means if your choice does not help you to get D and V, you make another choice. Make another choice. But remember, once you've chosen your Q, you are not changing it. So the only thing we are changing would be T, maybe, or maybe the D. But once you've said, I want my field to be F5, you're not changing that. You're just changing the other parameters so that these conditions are met. And we'll see examples. Now, so the D here is therefore called the CM discriminant, the complex multiplication discriminant. Now, this is just a repetition. This is just a repetition. We've already said that the order of the elliptic curve that is formed is supposed to be approximately this. 9aq plus 1 minus t. That one we've already said it. So there are just a few things we look at, and then we go to the example. Now, so we began by choosing q. Then we chose t. Then from our formula above, we've come up with d and v. Once this one have chosen, we now proceed and calculate what we call the Hilbert class polynomial. The Hilbert class polynomial. But before you do the calculation of the Hilbert class polynomial, you come up with a set SD. You come up with a set SD, and this set should comprise of elements A, B, C, such that A, B, C are integers, and these integers meet some condition. And this is a very important part. We'll be looking at this when doing examples. So you choose some integers. You're just choosing these integers, A, B, C. Those are 3 integers. And these 3 integers, you're not just choosing it randomly. Not choosing them randomly. They must meet some conditions. That the d we calculated above, the d we just calculated above must equal to b square minus 4ac. So you are choosing ABC, you're choosing ABC, but those ABC that you choose must meet this condition. That one, if you square B and subtract from it 4AC, it will give you the D you got above. And that is not the only condition. The other condition is that the GCD of these 3 numbers you're choosing must be 1. The GCD must be 1. And now, what about B? Supposing B is negative, not even negative. I'm just saying that the magnitude of B should be less than A. So the magnitude of, so A should be greater than B, that's what it means, or equal. A should be greater than or equal to B, that's what it means. But again, this A must be less than or equal to the square root of D, the magnitude of D, divided by 3. So take the magnitude, remember D was negative. Remember that our D was negative. So if D is negative, get the magnitude. Supposing it's 3, get the magnitude will be 3. Then divide by 3, then get the square root. So A must be less than this result and or equal to this result. It must be less than or equal to this result. And then A must be less than or equal to C. So C could be the largest of them all. A must be less than or equal to C. Remember that B here was less than or equal to A. And now the last condition is that if B happens to be negative, that is, if B is less than 0, then its magnitude should be less than C. No, should be less than A. And at that point, A must be less than C. So remember, these two are different. This is a case where B is negative. If B happens to be negative, then this condition follows. This condition follows that its magnitude must be less than A, and the A must be less than C. This is not less than or equal to. This is not less than or equal to. So if B happens to be negative, then this must be true. But if B is not negative, then consider this relationship. Consider this relationship. If B is not negative, then that B magnitude should be less than or equal to A. And A should be less than or equal to the square root of the discriminant over 3. And then A must be less than or equal to C. That is if B is not negative. But if B is negative, then we use this condition here. Okay. Now, so all these conditions, now we put them in our examples and then come up with elliptic curve. Of course, we have one small condition remaining. Now, how do you meet the above conditions we just talked about? The above conditions, how do you meet these above conditions? This for SD. How do you meet this above these conditions? How do you meet? Now, so this is how we meet the conditions. We begin by, first of all, getting A. We begin by, first of all, getting A. By this is the condition I'm referring to. So this is where we begin from. This is where we begin from. That's what I've written here. Calculate the A maximum. Calculate this, first of all. After calculating this, now, when you have A, okay, so let me say, for instance, this result here, this result here. Let me say it's 3.14. That I go to the discriminant and divided by 3, then the square root of that result is 3.14. What that means is that using this inequality here, less than or equal to, using this inequality, A should be less than or equal to that. It means A can be 0, A can be 1, A can be 2, A can be 3. So that's what it means. A can be one of these. A is one of these elements of the set. Now, so what you do is this, therefore. After calculating this A maximum, the maximum of A, and you find that the maximum of A is 3.14, it means, and that's what I've written here, that A then lies between 0 and that maximum. Now, once you discover this, now loop through, and this is how we'll be writing the code. Now loop through the integers of A from 0 to 3 to determine what B is. So loop through, it means, first of all, consider if A is 0. If A is 0. If A is 0, you come here, determine B. If A is 0, you see you already have D from above. You already calculated D. And now try and put A to be 0 here. So if A is 0, it means this part becomes 0. So you can get your B. That is, I'm just giving an example. Now, there are cases where you'll find that after substituting 0 here, and then you have B square is equals to A, you might find that this number D maybe has no square root. So if it has no square root, it means you cannot find B, because it must have a square root for you to get B. So if it has no square root, then it means A can never be 0. So you drop this option. It means A can never be 0. Now come to the next, and so on, and so on. So you're looping through all the integers of A, because I've said that A could be 0, could be 1, could be 2, could be 3. So try A to be 0, try A to be 1, and see what they can get B. If you cannot, drop that. Try A to be 2, and see what they can get B and C, and so on. Where you cannot get those numbers, it means A can never be that. So that's what it means, loop through integers of A. Now, so after looping through the integers of A, now consider to get B. consider to get B. And we've been told what B should be like. So after you got an B, after you got an A, that just let me say after looping through, maybe you settled on A being a 2. You settled on A being 2. So if A is 2, it means you can now get B, and B should be in the range -2 to +2. B should be in that range, the range of -A to +A. So after, then you see, if 2 is not range, it means you're talking about numbers like -2, -1, 0, 1, then 2. So again, you loop through all this to determine which one is B. You loop through all of them to determine which is B. Now that time you want to get C. So you have B and you have A. You come to this equation, substitute B, substitute A, and see whether C exists. Some cases you'll find that A does not exist. C does not exist. Some cases will give you C. So where C exists, and this I've written here, in fact, I've written here. So you're looping through every value of B, and you want to find what C is. Now, at the end of this procedure, you will have A, B, and C, and that's what we wanted. At the end of this procedure, you'll have A, B, C. That's what we wanted. That's what we wanted for us to be able to calculate the Hilbert class polynomial. So we say that for us to calculate the Hilbert class polynomial, first of all, we require this set. And I've just taken you through how to come up with this set. And then after you come up with the set ABC, you are now ready to calculate the Hilbert polynomial. And this is how we do it. This is how it's given. Now, just before that, you can see our D, you can see our B. You can see the D we came with, and you can see the A we came with. Now this thing, this fraction here, we are using this fraction to calculate the J invariant. That is what we should be using to calculate the J invariant. And to do this J invariant, I've said we will use the Rust program to do that. We will use the Rust program. So I'll be showing you how to do that. Of course, I'll be going through all the steps. Then when we reach here, we use our Rust program, and it gives us our J invariant. Now, after we have the J invariant, now we proceed and come up with the equation. We proceed and come up with the equation. So you'll go through all these the things I've written here, but I'm just giving a summary of the procedure. Once we have the J invariant, that we've just gotten there, and we'll be using our Rust code to do that, we now want to compute come up with the polynomial, the equation. But before we come up with the equation, we must determine whether the J invariant we just obtained gives us the order, the correct order that we want, the correct order of the curve. Because you'll be having J invariant maybe, and it doesn't give you the order. So you have to change the parameters above. The parameters, your B, your D, you have to change them. Because when you were determining B and D and, no, what was that? ABC, the set ABC. When you were determining that, I said you loop through A and find B. So while looping through A, you might find 3 options of B. 3 options of B. And while looping through B, you may get also 3 options of C. And now, in your calculation in the Rust code, you're only putting 1 option of B and 1 option of C and 1 option of A. So supposing that option has given you the J invariant, and then you come with that J invariant and try to check whether the order of the curve is what you wanted, because you wanted a curve of order 20. Then you discover it's not 20. It means you have to choose again that option of ABC. That option of ABC, and again use that to get the J invariant, another J invariant. But I'll show you an example where all these conditions are met. Now, there are cases. These cases are now common. These cases are common. And these are the cases we'll be using now to come up with our curve. After calculating the J invariant, check whether J naught, if J naught is not equal to 0, our J invariant is what I'm calling the J naught. If it's not equal to 0, or is not equal to 1728 mod Q, then you compute C1 using this formula. If J naught that you've just computed above using your Rust code is not 0 or is not 1728, then you calculate what we call C1. And this C1 is calculated as J naught out of 1728 mod Q, then minus J naught. So you can see it was not. So if it's 0, then you cannot do this calculation. If it's 0, you can never do this calculation because it just be 0 out of 0 minus 0. So you cannot do that. And again, if it's 1728, you cannot do it because it will be 1728 out of 1728 mod that, then minus, so it will give you maybe undefined. But we are saying that if it's not 0, then calculate C1. Now, after calculating C1, choose an arbitrary quadratic non-residue. What I mean by that, choose from elements of FQ one that does not have a square root. One that does not have a square root, mod Q. Choose one that does not have a square root, mod Q, and call it C2. And you can also choose another one that does not have a cube, and call it C3. Now, this only happens if you discover your J naught was not equal to 0 and it was not equal to that. So that is when you proceed with these steps. When you proceed with the steps I've just shown here. Now, the common cases of equations we would then have, the common cases are this, that if your J naught is not equal to 0 and J naught is not equal to 1728, then your curve, elliptic curve, is supposed to take this form or this form. If your J naught is not equal to 0 and J naught that you calculated using your Rust code is not equal to 1728, then your equation for the elliptic curve is supposed to take either this form or this form. Now, what about if your J naught is 0? If your J naught is 0, there are various options. That it should not be equal to -3, or it can be equal to -3. So if your J naught is 0 and is not equal to -3, then your form of the elliptic curve is supposed to be these two, either this or this. Look. Now, and this form, so look at this form. This form does not have A. This form does not have A. It only has B. And B can be 1, or B can be C2. Remember the C2 we chose above, and I'll show you how to choose it. The B can be C2 cubed. So that is a case where your J invariant is 0 and is not equal to, no, D. J, okay. J naught is 0 and the D, we calculate the D above. The D, we began by calculating D. So when J naught is 0 and D is not -3, then your equation is supposed to be one of these. So you choose one of these depending on how many points you want. Because these two curves would have different points. They would have different points. So if your points you want are met by curve 1, then you choose that. If they are met by curve 2, then that's what you choose. Now, the other thing that can happen is that you found your J invariant to be 0, and D above that you calculated was -3. If J was 0, J naught was 0, that is J invariant, and D was -3, then your curve is supposed to take any of these forms. It should be either this form, or this form, or this form, or this form, or this, or this. Look at this form. This form has no A. This form has no A. This form has no A. This form, in fact, it doesn't even have x squared, x cubed. This form has no A. And this form has no A. That has B. So you have seen curves that don't have A. That means while they were calculating, they discovered that the J invariant was 0, and their discriminant was either -3 or not -3. The discriminant is either -3 or not -3. The other option is that your J invariant will be 1728, but your discriminant will be -4. Your discriminant will be -4. So if the J invariant is that and discriminant is -4, then your curve can be any of these two options. Your curve can be any of these two options. You realize that this curve does not have B. It has A, 1. And this one also does not have B. So this happens when the J invariant is that. Now, so there could be a case where, just a minute. Now you have seen a scenario where the reasons why we have some elliptic curves that do not have B. They only have A on the right-hand side and X cubed. So these are cases where the was 1728, and either D was not -4 or D was -4. So if this -4, then your equation will take any of these forms. So when you are doing that, you just get your discriminant, and then you get your J invariant. Then after getting a J invariant, you come, okay, you had calculated your C2, you had calculated your C1 from above, C1 and C2 from above. Just come and substitute them. You choose one form here and substitute your C1 and C2. And then check whether that point, that equation would then have the points you want. If it does not have the points, you choose the other form. Now, so supposing you wanted 20 points, these forms will not all give you 20 points. One of them will give you 20 points, another will give you a different number of points. So you choose one that is right for you. And suppose you wanted 20 points, you come here. These forms will not all give you 20 points. One of them will give you 20 points, and the other ones will give you other different points. So you choose one that you want, depending on the number of points you want, because that is what you had in mind when you began constructing your curve. In your mind, you are clear the number of points you want the elliptic curve to have. So you choose one that is appropriate here. And I'll be showing you how that is done. So that is what I've just written here. I've said choosing the correct curve. You decide the proper, you've now chosen, you have those, supposing you have your J invariant and your D, you have several options. You choose one that has the number of points that you want. Let's look at an example. Let's look at an example. But what I've just written here before that example, I've said, normally, in case what normally happens is that after you've chosen your point, your curve, and come up with an elliptic curve, what normally follows is isomorphism, which we looked at. You want to map this curve to another curve. And then finally, this is the curve you now pick. This is the curve you now pick. And this is the curve that you have your specifications you wanted. This one, the one that has your specification. This one also has the same specifications, but normally we do, you do isomorphism, then you choose this. But these 2 points, these 2 curves would have the same specifications you wanted. If you wanted 20 points, this would have them, and this would also have 20 points. In fact, you wanted the field F, let me say F5. They are all on the same field. Now, so I just want to take you through an example slowly and see whether we can now, putting all the factors we just learned together, we go through an example. Now, I'm just beginning from what we know. We know this curve is y square is x cubed plus x plus 1. But we want to assume we don't know. Then we want to work on it until we arrive on this elliptic curve. That's what we want to do. But now, what is in our mind when what we are beginning by? This is our thinking. Our thinking is we want to create an elliptic curve on F5. This is our thinking. We want to create an elliptic curve on F5, and we want this elliptic curve to have 9 points. This is our thinking. So this is the information we have. And then we now want to proceed. We do not know what A is, although in our case we know what A is because this is what we want to generate. But now let's assume we don't know what A is, we don't know what B is. What we know is that our company wants to generate, to come up with an elliptic curve, and it wants an elliptic curve that has 9 points, and it wants this elliptic curve to be defined on F5. Now, if that is the information we have, we now proceed as follows. The first thing we did, okay, this one we've already agreed on it, we've agreed on that. Now, so the first thing we do is to calculate the trace. That's the first thing we did. We don't know this, we don't know that. We know that we want an elliptic curve on the field F5, and it must have 9 points. So let's now calculate the trace as we did last time. And the trace, we said that the number of points on the curve, we want them to be 9, should be the same as the field. Our field, we want it to be F5, then plus 1, then minus T. T is our trace. So when you make T the subject of the formula, crossing this, the other side of the equal sign, you have 3 is negative T, and so that means that T is negative 3. This is our trace, so we have it. Now, so we have our Q, and we have our trace, but what we want is the magnitude of the trace. Magnitude of the trace. Now, what you discover here, as we had already said, is that our T must prime to P. In our case, our P is 5, and you realize, of course, that they're already relatively prime. 5 and 3 are relatively prime. So we are okay to proceed. Now, so after that, we now have our Q. We have our T. We have our P. The next thing we did, we said, we would then calculate D and V. D and V. Let me take you back there. D and V was the next thing we were supposed to do. That was the next thing. After you've chosen your P, and you can see how easy it is actually. It's not anything hard. It's very easy. We just chose our P and Q. Now D is here. This is the requirement for us to choose D. No, we calculate D. D must be less than 0. That D must be congruent to 0 mod 4. Or if that is not the case, if that is not the case, then it must be congruent to 1 mod 4. And the other thing that we need to also take into consideration to get D is that the Q we chose, multiplied by 4, should be equal to T square plus the magnitude of D, the modulus of D times V square. Let's now go to our example and see how this works. Go to our example and see how this works. A very, very interesting thing. Very interesting calculations here. Now, so in our example, we have our Q as 5. We have our T as 3. And we want D to be less than 0. That's one thing you need to know. What were the conditions? The one I remember is D should be less than 0. And the other one I remember that D should be congruent to 0 mod 4. Or if that is not the case, then it should be congruent to 1 mod 4. And the other condition is this. So this is the one I'll go straight to and use first of all, and then I compare with this just to choose my right D. So I go straight to this condition. Now, so my Q is 5. 5 times 4 is 20. My T was -3. So -3 square plus D plus V. So what do I get? Take this, the other side of the equal sign, because this one gives you 9. The other side of the equal sign, that is 11. 11 is equals to D multiplied by V. Now, this one I'm using trial and error here. 1 to 6 number can be D, and which number can be V? So I'm just using trial. Of course, one thing I realize is that 11 is prime. I realize that 11 is prime. So the only possibility is that I can have D to be 11. And if D is 11, then V will be 1. V square will be 1. That is one possibility. The other possibility is that D can be -11, because I'm taking the absolute, of course, getting the absolute. This one I'm also getting the absolute. And then V can be 1 square. That is one option. The other option is that 11 can also be obtained by D being 1 and then V, and I don't know whether that is option. I don't know whether that is correct. We shall see. We shall see if 11 has a square root. If 11 has a square root, just a minute. If 11 has a square root, we shall see. Because if 11 has a square root, so you know what this means? This means that U is the square root of 11. That's what it means. Okay. Okay. Let me just remove this. That is what it means, because here, when I wrote 11 times 1, it just meant that 11, V square was 1. So I can obtain V, which is the square root of -1. Now, so the other option is that 11 can be equal to the absolute of -1 multiplied by 11, where now -1 becomes D. But now, which one meets the condition? Which one meets those conditions? Just a minute, just give me 1 minute, please. Now, so we have these scenarios. We have these scenarios for D and V square. And now you come to the other condition. The other condition was that D was supposed to be less than 0. supposed to be less than 0. So that condition then disqualifies this, that condition disqualifies this scenario and then disqualifies this scenario. So that the only scenario, therefore, is that D can be -1 or -11 or -1. Now, so the other thing we need to check is whether V can be, V square can be, whether V square can be 11. We are doing this mod 13. So in other words, you're asking, does 11 have a square root? Mod 13. That's what we're asking. So let me see. We have a code for verifying that. We have a code for verifying that, a code that gives us numbers that have square roots. Mod 13. I'm just looking for the code. Okay, this is the code. This is a code for getting numbers that have square roots, mod 13. So we had looked at this code earlier when we were looking at quadratic residues. That was earlier. And let's see whether 11 has a square root. Mod 13. So this code is telling us numbers that have square roots mod 13 are only 1, because its square root would be 1. Then 3 will have a square root, 4 would have a square root, 9 will have a square root, 10 would have a square root, and 12 itself will have a square root. But 11 does not have a square root. So since 11 does not have a square root, it means this other option is also not the right option. This option is not also the right option. So we're only left with this one option, that D will be -1, 11, and V square will be 1, which means that V is 1. So you can see how you come up with the D. That is how you come up with the D. That's how you come up with the D. Using the conditions we were given. So our D now, we are comfortable that our D will be -11 and our V square will be 1. That's what I've written here and said that since 11 is prime, the only solution is supposed to be this and that. But when we've seen it will not work. So when we choose this one worked. But you can see what is, does it verify? What is 11, -11 mod 4? It also accepts -11 mod 4 will be that. So it means this is a correct D, and our correct V is that. Now our correct V is 1. Now, so you've seen the scenario, how we came up with various options of D and how we disqualified some of them because of the conditions that we had been given. Once you have this D, you now want to calculate the Hilbert class polynomial. Now, how are we calculate the Hilbert class polynomial? I take you back, just again, you see the conditions of getting the Hilbert class polynomial. Here, we said, for us to calculate the Hilbert class polynomial, the first thing we do is we choose integers ABC that meets these conditions, that D should be equal to that. The GCD of these three integers should be 1, and the magnitude of B should be less than A, which should be less than this, and A should be less than or equal to that. And if B is less than 0, then this must be met. So that's how we want to proceed and calculate the Hilbert space the Hilbert class polynomial. That's why I want to proceed. So far we have Q. So far we have D. We have T, and we have P. So we now want to find ABC. And ABC are the ones we'll now be using to calculate the J invariant. Those are the ones we'll be using to get the J invariant. Okay. Now, for us to get those conditions ABC, the first thing we said, and I remember saying that, we find maximum of D and maximum of A. Maximum of A is given by the square root of the D out of 3. Our D we just found to be 11, negative. So when you put in the absolute value, it will just be 11. So 11 divided by 3, then the square root will be this. The square root will be that. So that means we choose A should be 0 or 1. Values that are less than this number. This is 1.9. So values that are less than this number are 0 and 1. So A can be any of them. In some cases, it could be both, but we want to check whether it will be both, because then it must meet other conditions. Let's check whether A can be 0. Whether A can be 0. So we then check the other condition, that B should be less than or equal to A. Should be less than or equal to A. So if A is 0, then it means that B is 0. It means that B would be 0, because it is only 0 that is less than or equal to 0. But now, is this possible? Is this possible? Is it possible that we can have A that is 0 and B to be 0? So we come to this and see. We come to this other condition and see whether it's possible to have A to be 0 and B to be 0. So if A is 0, it means this part is 0. And B is 0, it means this part is 0. So it means we have negative 11 is equals to 0, which is not possible. And of course, it's also possible. We can also not, if A is 0 and B is 0, we cannot get C, because we require ABC. We require ABC. So if A is 0 and B is 0, there's no way you can get C. So it means, therefore, A cannot be 0. So I've said that A, therefore, 0 for A, 0 is not valid. So we try 1. We try 1. That's why I said you look through all the options. Let's look through. So we try 1. We try A to be 1. So if A is 1, then we know that B is supposed to be less than or equal to negative 1, less than or equal to negative or 1. That's what we said. B is supposed to be in this range. Now, so that then means that B can be negative 1, can be 0, can be 1. B can be any of these. Now, I want to check which one of these will then be B. Which one of them will be B? Let's check if B can be negative 1. If B can be negative 1, we have this condition. The condition said that if B is less than 0, then the magnitude of B should be less than A. Now let's see. If B is negative 1, then we use this condition, because B is less than 0, is negative. So if B is negative, that it's less than, not equal to, not less than or equal to, should be less than. But you see, the magnitude of negative 1 is 1. So it does not meet this condition. Because 1 is not less than 1, 1 is not less than 1. Does not meet that condition. So it means B cannot be negative 1. Now we check whether B can be 0. We check whether B can be 0. If B is 0, again, we go to the equation that it says, this is the equation. The equation that it says negative D, or just D, says D should be equal to B square minus 4AC. That's what it says. So our D is negative 11, our B is 0 square minus 4, A is 1, then C. So this one, it means you have negative 11 is negative 4C. We are doing this mode 13. You cannot find C. In this case, you cannot find C. C cannot be obtained. Mode 13. So we are left with only one option. Let's try it and see. Let's try it and see. B to be 1. Let us see if we can obtain C. Negative 11 is B square minus 4AC. So negative 11, if B is 1, this will be 1 square, which is 1, then minus 4C. So this one crosses the other side, it becomes negative 12 is equals to 4C, no, negative 4C, which means that if C is 3. So C can be obtained. C can be obtained if B is 1. Now, so that therefore means we have our set. Our set ABC, A was 1, then B is now 1, then C we just calculated is 3, and you have that set. So once you have the set, you now go to your code, and your code, you have your negative B plus the square root of D, then divided by 2. And remember, our D is negative here. So now you want to get the J invariant at this point. So the J invariant at that point is now what will send you to choose the type of curve that you want from the types we have. Now, so let me go to my code and get the J invariant. Get the J invariant at this point. At this point, this is just the same as negative 1 plus I. I is a complex number. Then square root of 11. Square root of 11 over 2. This is what I've just written here. How does I come in? We know that the square root of negative 1 is I. The square root of negative 1 is I. And we know that negative 11 can be written as, the square root of negative 11 can be written as 11 times negative 1. And this is the same as square root of 11 times square root of -1. But the square root of -1 is I. So that's why you see is I, then this one remains. Now, so these are what I put in therefore in my code. Okay. So this is my code. It's a very short code. In fact, what I've just told it is that I want to get the square root of 11. I'm doing it using F64, the square root of 11. Then there is tau complex, -1, and the square root of 11 divided by 2. -1, square root of 11 divided by 2. That's a formula. That's the formula that we had. That's a formula. The formula for doing the J, our D, it was -b, which is -1, and then the square root of 11 over 2. That is our formula. Now, so, okay, I added something here, which we call the Q expansion. I don't want to go into the details of Q expansion. But now using this method, we're able to get the J invariant. The J invariant is -32, 768. -32, 768. Now, look at my Kaggle TOML. I'm using a big integer. And now when you're using this big integer, you don't get very accurate results. But for my case, this is an accurate result because I asked it to approximate. But you can use RAG. You can use RAG. If you are using RAG, I didn't want to use it because I've not installed it. And I saw the process was taking a bit long to install. That one will give you very accurate results. But for my case, this is a very accurate result. This is the same result you would get if you had to use so when you're using this big numbers, then you must import a number complex. This one is just assisting you to do -I and so on, taking care of -I, taking care of I. This one takes care of I, because I is a complex number. Now, so we have gotten our J invariant as -32, 768. -32, 768. Now we go back with it, and it will assist us to choose the curve from one of the formats we had. It assists us to choose one of the curves. Now, so this is what I have. This is what I got. -32 was -32. But remember the formula for Hilbert class is this. It's X minus the J invariant. But the J invariant we found to be -32, 768. So this negative and this negative is what gives me positive. So this is what I now have. Now, this is what is important here are these coefficients. The coefficient of X and this 32, 768, because I want to reduce them mod 13. I want to reduce them mod 13. And when you reduce them mod 13, now if 13 were to go here, the remainder would be 1. If 13 were to go here, the remainder would be 3. So this is now what I have. Now, so after getting this is just a polynomial I was looking for, the Hilbert class polynomial. Using this Hilbert class polynomial, I want to find out what is x. What is x, so that this will give me. Oh, okay. I was reducing this mod 5, not mod 13. Mod 5 because we are doing it. We are in the field F5. So I'm reducing it mod 5 because the field is F5. That is how I came to the remainder of 3. Now, I want to find x. X should be a value which, when added to 3, gives me identity. That value is 2. So this is now my j. This is now my j. And I've just explained what it is. Now, so j is 2. J is 2. So it is not 0. And it's not this. So if j is not 0 and is not this, we say that we compute C1. We compute C1, and this is how we compute C1. If you check the formula above, we say it to be J naught out of 1727, no, 28 minus J naught. That was our formula. J naught out of 1728 minus J naught. So when you do this, this would be 2. This one mod 5. Mod 5, this is 3. So this gives you 2 out of 3 minus 2, which is 2. So our C1 is 2. Our C1 is 2. What was our D? Our D was negative 11. Now, so where you find that you see in this case, we have not computed C2. So since we've not computed C2, we go to the conditions of the curves and check which curve we should pick. Which curve we should pick. Then we come and insert our C1 and the C2. But in our case, we don't have C2. So we just go back and check which curve. If J is 0, which curve should we choose? If J is not 0. And what was our D? So we go back and check the curve. These are the curves we're supposed to choose from. So you look at the cases and look at which case favors you. So in our case, J is not 0 and J is not 17. J naught is not 0. J naught is not 1728. So in that case, it means our curve would take this form or this form. We try both forms, and we want to see which one will give us the 9 points, because we wanted a curve that will give us 9 points. So this form is x cubed C1x plus 2C1. And this other form is x cubed plus 3C1, and then multiplied by C2 square x plus 2C1 multiplied by C2 cubed. So let's try this form first of all. The one of this one is x cubed 3C1, then 2C1. I just want to try that and see whether it gives us 9 points. If it doesn't, then we check the other form. Okay, so the form that we are trying is the one that is said x squared is equals to x cubed plus 3c1 x plus 2c1. But in our case, our c1 we found to be 2. So this will be 1. This is 6. 6 mod 5, this is 1. What about this? This will be 4. Now we use our Rust code and see whether this one has 9 points. Whether it has 9 points, and I have Rust code for confirming that. Or supposing you're dealing with a very big field. See, this is x cubed. A is 1 and B is 4. Mod 5. A is 1 and B is 4. Mod 5. A is 1. A is 1. B is 4. Mod 5. We want to see whether this curve has 9 points. And if it has 9 points, then it's the curve we are looking for. You only need now to do isomorphism. So let's do Kakoran. Okay, Kakoran has generated all the points and has told us the order is 9. Generated all the points and has told us this curve has 9 points. So it means we have obtained the curve we wanted. We have obtained the curve we wanted because it has 9 points. We wanted to have 9 points. It has 9 points. So our curve is x cubed plus x plus 4. And I said the final step, after you've obtained this, you do isomorphism. You map it. You map it to another curve. And isomorphism says that you can obtain, to map that curve, you map it to x cubed plus ad square x plus bd cubed, where d is a number mod 5 that has a square root, a number mod 5 that has a square root. There are several numbers that have square root mod 5, that I've chosen 4. Because 4 will have a square root to have 2 and -2, the square roots of 4. But we have several numbers. So you can choose this. If it fails to give you what you want, and again, you can choose another. But let's choose 4. So multiply 4 by a 4 square. So what was our curve? Our curve was y square is x cubed plus x, then plus 4. So while there is a here, multiplied by 4 square, there will be 16. So that means y square is x cubed plus 16x, then plus 4 cubed. 4 cubed times 4. I'm just putting this square here, and I'm putting this cubed here. So this square will be 4. That's how I get 16. What about d cubed? My d is 4. So this means 4 times 4 cubed. I don't have a calculator, so let me just say 4 is -1, 4 is -1, 4 is -1, 4 is -1. So -1 multiply 4 times will be 1. So this is y square is x cubed, and this mod 5 again is 1, and then that is 1. So we've obtained the curve we were looking for. When we began, we assumed we don't know this coefficient, and we don't know this coefficient, and this is what we've been looking for, and we obtained that curve. So this is how we arrive at it. This is how you come up with a curve from the scratch. So there's another example, but today I'll not show it because of time. So I think again, tomorrow we look at the same thing, we revisit the same thing and look at the other example so that we can see cases where, for instance, supposing you got, when you are calculating the Hilbert space there, supposing you got different values of J, which are correct. Suppose you got a 2J invariants, what will then do? So I would, or you can even get 3, you can even get 3J invariant. So how do you proceed from there? That is what I'll be looking at again in the next example. But in the next example, then we'll do it next time. Okay, thank you.